Hello guys, welcome back to the YouTube channel. Today we are going to discuss the chapter chemical bonding and molecular structure, some concepts of those which are very tricky. So first let's go to resonance structures, the rules that apply to create resonance structure and the stability among various resonance structures are the topics that we're going to discuss. So first let's discuss the rules. So the first rule is all the resonance structures should have the same number of bonding and non-bonding pair of electrons. So this I can illustrate this with a simple example. All of you know the resonance structure of ozone looks something like this. Instead of representing a coordinate bond, if I put a plus and minus, this has two lone pairs of electrons, this has one lone pair, and this has three lone pairs. Now, if I make another resonance structure of this by transferring one lone pair of electrons to the bond pair, and I draw something like this. As you can see, the number of bonding and non-bonding electrons in this structure and this structure are different, whereas the actual resonance structure of ozone is this. So this is an acceptable structure because over here also there are three bonding pairs of electrons, over here also there are three, but over here there are four bonding pairs of electrons. So obviously this is not an acceptable structure. So that's all about the first rule. So we can say that this structure is not acceptable. Moving on to the second rule. The second rule states that the position of the nuclei should remain same in all the resonance structure. So let's take the resonance structures of the carbonate ion CO3 2 minus. This would be the initial structure, and the other resonance structures involve changing of the double bond. But I can't draw a structure in which O is a central atom and then carbon goes somewhere and oxygen goes somewhere else. And this can't represent a resonance structure of the carbonate ion because in this the position of the carbon nuclei has been changed and even the oxygen nuclei has been changed. So these are not acceptable resonance structures. And the last rule, which is the most important and most frequently used rule, is that the octet rule can't be violated. So this can be illustrated in an example like this. Suppose I have an ether uh, which is like this. Then I decided to transfer this bond pair over here and I make a structure like this. Such a structure is not acceptable simply because the oxygen atom over here has 10 electrons around it. 1, 2, and 3 bond pairs which contribute to 6 electrons plus 2 lone pairs that it has. So 6 plus 4 is equal to 10, and since it's violating the octet rule, this resonance structure is not acceptable. That was all about the rules for creating a resonance structure. So next, let's move to the stability. So among the given resonance structures, the most stable one is one in which all atoms have a complete octet. There is less separation of charge and there is more dispersal of charge. Now you would be thinking that both these points mean the same, but actually it's not. Less separation of charge refers to that the negative charge is present on the more electronegative atoms. Suppose there's a bond between oxygen and carbon. It's preferable that oxygen gets a negative charge if a negative charge has to be there, and carbon gets a positive charge. That's the more electropositive atom among the two gets the positive charge. So such a structure would be more stable than a structure having O with positive charge linked to C with negative charge. This indicates more separation of charge. Whereas more dispersal of charge, as you can see in the carboxylate ion, refers to this, where this negative charge can go here and the bond pair shifts to this. So the charge on the first oxygen atom, that is this one which had negative charge, has now got dispersed and now it no longer has a negative charge. So this refers to more dispersal of charges, there is less separation of charges is this. So we're done with resonance structures. Next, let's move to the concept of dipole moment. So let's continue with the concept of dipole moment. So the first topic I'm going to discuss in this is Debye versus ESU. So this is a conflict between the choice of units. So another commonly used unit for dipole moment would be ESU, and you would know this if you had solved some previous year questions. But Debye is the unit that's given in NCRT. So all you need to know to solve questions involving ESU is the relation between Debye and ESU. 1 dBi is 10 power minus 18 ESU. This states that ESU is a larger unit than dBi. And next we'll go to the convention and arrow direction. So in chemistry, in this chapter, we learned that the direction of the arrow of dipole moment is from positive to negative. Simple logic behind this is that it's the the more electropositive one that donates electrons to the more electronegative one, and this is the direction in which electrons go. But in physics, the arrow is from negative to positive, and that's simply a convention that we use while representing dipole moments, as you will learn in class 12, the first chapter, that is electric charges and fields, in which the concept of dipole moment is introduced in physics. So in order to avoid confusion, you just remember the chemistry logic that electrons are moving towards the more electronegative element, so the arrow is in negative. And in physics, it's the opposite of it. So that's all about dipole moment. Now, there are a few other concepts left in this chapter, which we'll discuss in the part 2 video. Thank you so much.
Please do like and share the video and subscribe to our channel.